Yeah, that's mine. This is the one I brought in. This is mine, and these two were here, but I don't know. Yeah, sure. Yeah. Okay. Well, it does change a lot of things for everybody. We are in a network, man.
Good afternoon. It's my pleasure to present the next speaker, uh, Professor Patrick De Leenheer from Oregon State University. He's worked in a wide variety of problems in mathematical biology. I'll just cite some very quickly, almost at random. Virus models, chemotaxis, quorum sensing, evolution, optimal placement, chemical reaction networks, and monotone systems. All this from your CV. And he's also currently an associate editor for Mathematical Bioscience and Engineering. So it's our privilege to hear him talk today on the subject of Ross-Macdonald malaria model.
Thank you. Thanks for inviting me. It's my first time in South America. So if I say stupid things, it's because I'm not used to the Southern Hemisphere. Okay. So this is not as well developed as Michael's talk, where he spent many summers thinking with his eyes closed. This is much more recent and somewhat unfinished. It came out of a project that a student was working on when I was at the University of Florida. He was a student in biology, Nick. Well, I'll put up his name in a second. So Nick was interested in malaria, understanding malaria, the spread of malaria, and that led us to the work I'll present here. Yeah, and Dave Smith was a co-advisor. Nick is currently a postdoc in the UK, as you can see. Okay, so so before we do some mathematics, I'm first going to describe a little bit what malaria is, and not that I'm an expert in the first part at all. I actually pulled this off of the websites that you see up top there, the World Health Organization and the CDC. It's somewhat of a mix of information I found there. So it's a parasite, and there's 5 ones apparently, but the most dangerous ones for people are P. falciparum and Vivax, and it's a vector-borne disease, so it goes from a human to a vector to a human, and it has to make that transition. There are some exceptions that I read where it can go directly from a human host to human host, for example, but we won't consider that here. And what it does to us, to humans, is that it kills our red blood cells. After it goes through a very complicated life cycle, none of that will be discussed here either. That's a fascinating story in itself, just a within-host infection mechanism of malaria, because it goes through many different stages. And the symptoms are fevers and chills and flu-like symptoms, and they occur after, about a week or two. And that's the time it takes to go through that big big cycle. So the risk, I was kind of shocked by this number. That's almost half of the world's population of people are estimated to be at risk. But predominantly it's sub-Saharan Africa that has the highest burden. So 90% of the cases and the deaths occur there. That's astronomical, obviously. And that's because they have very active mosquitoes there that are also good at defeating, that are good at whatever we're trying to do against them. And then the prevalence, so in 2015, there were about 214 million cases reported, and then 500,000 people died worldwide. Okay, so here's a little bit, what do we do about them? What is a control strategy? So there's a prevention phase. So we can use insecticides and indoor spraying and bed nets that are treated with insecticides. ITNs is a short acronym here. And then there's a treatment. I forgot what the A stands for. Probably some experts know it. What was it again? There you go. Combination therapy. The difficult word I can't remember, but okay. All right. So you see my ignorance here, but I promised you I didn't know much about the first two slides. But treatment is also in danger because there's resistance report. The same holds for the spraying, by the way. These mosquitoes develop resistance. And so there's quite a bit of activity in trying to find a vaccine. And what I found were these, just Google, that we would hear about a drug that was or a vaccine that was close to being ready. Here's the name. But I don't know if it is. This was end of last year. Some announcement would have been made, but I haven't seen the announcement. So maybe I'm looking at the wrong sources. But and this particular one was developed in a sort of a joint thing between GlaxoSmithKline and then a global nonprofit. And Bill and Melinda Gates Foundation are supportive there as well. Okay, so a little bit of the history here. In my title, you might have noticed, am I speaking loud? Can you hear me? Okay. So if there's any questions at any time, please don't wait until the end of the talk. You can ask me, interrupt me whenever you feel like. So this goes back to this person here, Ronald Ross, who won the Nobel Prize in Physiology or Medicine in about just over 100 years ago. And so these are quotes that I've pulled from the Nobel Prize website. And there's two quotes. The first one is, well, here's the reason why we give you the prize, right? So imagine you don't know what malaria is. Well, he elucidated how it enters the organism and so forth, and how that cycle goes. And it is a very complex cycle. But then it goes on and says, but perhaps the greatest contribution was the development of mathematical models for the study of the epidemiology. Okay, so as mathematicians, not all hope is lost. Apparently, you could perhaps aim for the sky. And so I thought maybe that was those days. I don't see that happen these days, but then the actual analysis, the mathematics of the model that Ross is famous for were done by Alfred Lotka a little bit later. And yes, it's the same Lotka that we all are familiar with when we study our first or second ODE course and encounter the Lotka-Volterra competition or predator-prey system. So Dave Smith, the co-advisor of Nick, pointed that out to me and actually sent me the paper, or actually this is just the table of contents of the paper where that analysis is performed. Okay, so if anybody wants it, I have it now. It's interesting. He tries to actually approximate solutions, and a little bit like what you do when you teach the Frobenius method to find series solutions of differential equations. He does that here. So he does more than what we would now do with a regular phase plane analysis. Okay, and then there's a second name, McDonald. I only have this to tell you about him. I looked a little bit, but the main thing seems he was improving Ross's model in the 50s. I cannot tell you what improvements they were. I forgot. But in any case, he was somewhat the driving force for the WHO to start using DDT, which afterwards had to be pulled back because it wasn't too healthy for us either. So, but that's an insecticide that was aimed at killing the mosquitoes. Okay, so and today when you go into the literature and you type Ross-Macdonald in any search engine, you'll find various different models, but they're all somewhat variations on a basic one that I will present to you today. And so there's not a unique Ross-Macdonald model. I just want to say there's a collection of Ross-Macdonald models. Okay, so what we will do is use a very simple one as a building block to construct a more realistic model. It's a patched model, like Michael was giving us examples of earlier on, with the focus on three particular issues in mind. So one is to include or incorporate environmental heterogeneity. That's the patched nature. Okay, then to address the mobility of both the humans and the vectors. Okay, and then to see what the consequences of these two features are on control measures. And in fact, there was another, well, maybe not. We'll get to that. Okay, so here's that basic, simple Ross-Macdonald model. So capital X and Y denote the number of infected humans for X and mosquitoes for Y. Okay, and we will assume that those two populations, humans and mosquitoes, are constant, and that you can either be in one of two states. As a human, you're either infected or you're susceptible. As a mosquito, you're infected or susceptible. Okay, but the total population is constant, and those constants are H and V. H for human, obviously, and V for vector, not for mosquito, clearly. So, of course, we could write down the equations for the susceptible humans and susceptible vectors, but that would just be trivial because of the constancy of the total population. So we can just ignore those two equations and stick to these. Okay, so there's in each equation has two particular terms. Let me start with the two last ones. They're the easiest ones to explain. They're linear death rates in a broad sense. R is actually the recovery rate. So if you're infected as a human, you can get rid of the disease, right? If you survive, if you're lucky enough to survive, and 1/R would be the expected time it takes for that to happen. Mu is the death rate of infected or infective mosquitoes. Then the first two terms are really the infection terms. There's a whole bunch of parameters in here, but really it's a mass action kind of idea that you see. It's a product. So you have to have a susceptible of one population meeting an infective of the other population, right? And the susceptibles are just H minus X and V minus Y. Here's V minus Y, here's H minus X, right? And then there's other parameters. A is the biting rate. So that's just, you can experiment with that, I guess. That's the number of times a mosquito would bite a human per unit of time. So you stick your hand in a box and you see how many bites you have after half an hour or so. And that's what A is, right? B and C are probabilities that an infectious bite occurs from a vector to a human and from a human to a vector, respectively. So some bites of an infectious host will lead to an infection in whomever the transmission is going to. but not all of them do, and the probabilities are B and C respectively. And then this T is the incubation period. It has to do with this complicated cycle. When we are being bitten by a mosquito, it takes some time for the life cycle to, for us to be able to transmit it further on. But similarly with the mosquitoes, there's a delay here, and that's what explains this exponential. So if the incubation period would be 0, then that would be 1 here, and you wouldn't have that delay sitting there. But this arises from a quasi-steady state approximation of a 3-dimensional model where you look at infectious or infected but non-infectious mosquitoes as well as infectious mosquitoes. I don't want to spend too much time on that. We're making a simplification here. Okay, so we're first going to scale this model since the total populations remain constant, H and V. I can divide the capital X by H and the capital Y by V, and I get proportions. Little x and little y are proportions of infectious humans or vectors, right? And that's a standard exercise to do. Usually you scale in order to reduce the number of parameters in a model, because the more parameters, the uglier things look, and you want to see what is really not the parameter that's important, but the parameter combination that's important. And so we do this, and we lost a few, but we actually gained one, which is little m. And little m is the number of vectors, total number of mosquitoes divided by total number of humans. That's sitting right here. But then the mass action terms look nice and easier. Okay. So now this is a 2-dimensional nonlinear system. It's actually, do I mention that here? No, I don't mention it. Okay. So x and y are proportions, right? So this lives on the cube, on 0, 1 squared, right, in the plane. So it's a planar system, but its state space is actually the cube in the plane, right? So we restrict all the solutions there. It's obviously an invariant set, otherwise the model wouldn't make sense. Trust me, it is. So it turns out that you can define this notion. When I walked in, Michael was putting up a slide about R0, and he said, well, Patrick might talk about this. Well, I'm not going to in this context, but there's this important notion of basic reproduction number that you can define in various ways. Let me cut that short story, because later on for the more complicated model, we'll return to it. So it's a fraction, a ratio of various parameters involved in the model, right? And it turns out that the dynamical behavior depends on whether this number, the basic reproduction number, is less or bigger than 1. Okay. So I also highlight another parameter, alpha here. It's A times C over mu. That's the number of expected successful bites. So think, okay, so let me break it down. So suppose you have a susceptible vector mosquito, right? And it lives, well, how long? Expected is 1 over mu. 1 over mu sits here, right? And then it's going to be biting, right? It's biting at a certain rate. And multiply that by the probability that it actually picks up the infection from a human. Then you can interpret that parameter alpha. The reason why I'm talking about it, in addition to R0, is once you look at the steady states, you can simplify them quite quickly. So first of all, 0, 0 is always a steady state. That means there's no infection. Okay, both the vectors and the humans none of them are infected. That's always a steady state. Just plug in x equals 0, y equals 0, and both sides here are 0. But then there can be a second one, an endemic steady state, which is explicitly computed here and written in terms of the parameters above. And of course, if this is to be positive, clearly R0 should be bigger than 1, right? So this only exists if and only if R0 is bigger than 1. And it's actually in the cube, I should say, but that's easier to check that that's the case. And then Okay, so just for reasons that hopefully will become clear a little later, I do a sort of inversion here. So I look at X bar, if there's this second steady state, this endemic steady state, meaning if R naught is bigger than 1, then this X bar is equal to that, and I can invert that formula and find R naught in terms of X bar. That's what I'm doing here. Right? And it shows you that R naught can be written as, you know, some expression involving X bar. That's the proportion of infected humans, as well as a parameter alpha, and that's all you need. So if you know these two parameters, and imagine having a malaria infection somewhere, you can go to the hospital and say, how many cases are there? Right? Well, they'll tell you 500. You know the city's population, divide by that. That's your proportion, or at least a lower estimate of a proportion. So, and if you know what alpha is, this parameter we just discussed, and you can simply derive what R naught, the value of R naught. Okay? We'll do this for the patched model. So we'll have a vector of R naughts, one for each patch, and then we'll try to do a similar inversion process. Okay, so here's the global behavior. You can derive this in various ways. The simplest one would be through phase plane analysis, but you could use the theory that Michael referred to of monotone dynamical systems, which will feature more prominently as we go along. And that's the one I used actually to, you know, summarize the results. So the behavior is very simple, right? There's a dichotomy. There's only two things that can happen. If R naught is less than or equal to 1, all solutions, then there is no endemic steady state. There's only the zero steady state, and all solutions converge to it. Okay. So the infection simply gets cleared. If R naught is bigger than 1, then all non-zero solutions will converge to the endemic steady state, and the infection persists. Very simple. That's why probably this was such a successful model. Nice, has a nice simple dichotomy. Okay, so, well, suppose you have an infection, meaning R naught is bigger than 1. How do you control it? Well, make it less than 1, right? According to the dichotomy, if you succeed in doing that, you'll get rid of your disease. That's why this theorem is useful, right? If you didn't have this theorem, there was no guarantee that making R naught less than 1 would lead to infection control. Okay. So we look at our definition of R naught, all these parameters. Well, it's a fraction. Well, if I want to decrease it, then either I want to decrease any of the factors in the numerator or increase any of the factors in the denominator. That's what I'm saying here. How do we do that in practice? Well, interpret it. A is the biting rate. Well, put bed nets in so the mosquitoes can get to you and therefore cannot bite you, right? Decrease M. M is the number of vectors per host. Well, that's kill the mosquitoes, right? You can't killing the, well, you could try to make more people, right? That's one control strategy. But the obvious one, and that's the one that was, you know, in fact, I heard a shocking, maybe a small anecdote. In California, there's Bakersfield, I believe. In that area, there's oil. There was an oil industry, and they would have leftover oil. And when the mosquitoes were bothering them too much, they would go to the water bodies and just dunk in diesel fuel and stuff like that. This is 50 years ago. It wouldn't work anymore now. But that was killing mosquitoes. And then B is a probability that an infectious bite occurs from a vector to a human. So that could be done by vaccination or prevented by vaccination, for example. And then the increasing, well, R, increase the human recovery rate. Well, if people take drugs, they will recover quicker. Increase the mosquito death rate, so kill them. And the incubation period. I'm not sure how you would do that in practice. How you could, yeah. Okay, so so now we'll get back to the goal originally. So far, I'm just summarizing what was well known. And now we'll get back to the issue of what about environmental heterogeneity, and what about movement of hosts and vectors. Okay. Okay, so the way we're going to model this is by saying there's n patches. N could be an arbitrary number. Think of them, and the scale could be, it depends on who you are. If you're working on a global scale, it might be countries. Okay, if you're working in a province in sub-Saharan Africa somewhere, it might be little towns that are connected. Or it might simply be a village and the houses where, you know, various families live and have cases of malaria occurring. So that depends on who you are, what those patches are, what those geographical meanings are. But each of them, imagine, obeys this simple model with its own set of parameters. Those parameters can change depending on which patch you are in, right? There might be super mosquitoes in one patch that have a much higher biting rate than in another patch. So they will have a higher A than the patches where the mosquitoes are lame, right? That's just one example. But okay, so and now we assume that both the humans as well as the mosquitoes can move between these patches, but we'll do it in a very, it took me a while to get used to this. I saw this in a paper by Chris Cosner, 2008, Math Biosciences, I believe. So individuals, be they vectors or humans, will be residents of a certain patch. So they will have their home. But then they will, during the day, they will travel to other patches where they can either infect, if they have the infection, they can infect the residents there, or they can pick up the infection from an infected resident there, right? And the way this is modeled will be clear later. This is different from, for example, the diffusive coupling models where individuals actually move around and they don't have a residence patch, but once they move, they are residents or of the place they went to. They moved effectively. Okay, so that's a different type of modeling. I believe the name, I believe Chris was mentioning this as Eulerian. So our approach is called the Lagrangian approach, and then there's the Eulerian approach, which is the other one. Okay, just so we are aware of this. How are we going to do that? Well, we're going to specify the proportion Pij of time that a resident of a human resident of patch I spends in patch J, right? And so we get a matrix, an n by n matrix with non-negative entries, right? Those proportions are non-negative entries, and they have to add up to 1. If you're a resident of patch I, you have n minus 1 patches available, including n in total, including your own, but you have to divide your 100% of time among all of these, right? So this will be a matrix that has a property that's it's a row stochastic matrix. Okay? It's a non-negative matrix whose rows add up to 1. And the same thing happens for the mosquitoes, but the mosquitoes may have very different mobility patterns. That will be captured by a similar row stochastic matrix Q. Okay? And we'll see that so special cases that have been considered, including by us, that's how we started, is to say, well, suppose the mosquitoes don't move, right? And then you then Q is the identity matrix, right? 100% of the time you're sitting in your own patch. You're sitting on the balcony and waiting until some human passes by and you try to bite him, right? So as soon as Q or P deviates from the identity matrix, there is genuine movement occurring. Okay. Now, it turns out that when either one of the population is supposed to not move, the results are kind of what you expect. When both move, things get more interesting. And somewhat unexpected control implications for control will occur that we will point out as we go along. Okay, so here's the model, the patched model. So there are two n equations, right? One for the n for the host, n for the vector. And so what we have here is this is the proportion of susceptible humans that of patch I that can spend their time in other patches J. Pij is the proportion they spend there, where when they get bitten by a J resident mosquito and the infection is successful, and we keep the incubation period into account times this total number of J mosquitoes, sum over all the possible patches gives you n infection terms rather than a single one. And the same happens for susceptible mosquitoes that might be visiting other patches where they can be infected by infectious humans. And then they have their recovery rates and death rates here. Okay, so the infection rate, that's this thing in the, really the product, but it's an average of the infection rates across the patches, which is weighted by the proportion of the time that they spend in these patches. So if the PIJs are bigger, then that rate has a bigger weight in this sum. Yeah? Which makes sense, right? I mean, if you spend more time in patch 1, much more time in patch 1 than in patch 2, then the contribution of infection should be higher there. Okay, so same exercise, scaling. Now we scale all of the patch numbers into proportions, and we make all the vector numbers into proportions. And we introduce this scalar Mij, which is kind of weird. It divides the number of, it takes the number of, total number of vectors in patch J and divides it by the total number of humans in patch I. Okay, so that's right here. The patch characteristics, same thing as a single patch model, same expression. Only some subscripts were added to refer to the appropriate patch, in this case J, and then alpha J, that other parameter that was important. And so just to introduce some new terminology, we'll call the J patch a sink if that R0, that reproduction number, is less than or equal to 1, because if there wouldn't be any other patches, we know from the dichotomy that everything would go extinct, right? The infection would be cleared. So the terminology of sink is somewhat natural, hopefully. And it's a source or a hotspot if that R0 would be bigger than 1. So if there wouldn't be any coupling, we know exactly what would happen to each of these patches with the result of the first dichotomy that I showed you earlier on, right? But now things have changed because of the coupling. And, okay, so, oh, yeah. So I'm going to do a little extra work, which you might think is redundant, because we did the scaling here. We could go to work and work with this model, and that's effectively what we will do. But I have in mind that inversion problem. Remember what that was? Measure the number of infected humans. Can you invert and find R0? So that's what I'm going to try and do here. This is one reason why I'm doing further manipulations. There's nothing deep going on. But I just want to point out here, maybe I should have highlighted this in red, R0J appeared here. The R0 appeared into the model explicitly. Rho J is rho for ratios of the jth total human population over the first total human population. Okay? And that appears here as an inverse, and here, and yeah. Okay, now the state space is the cube in 2 n-dimensional Euclidean space. Yeah? And the system is strongly monotone. Maybe I should say what that means, because I will take advantage of, yeah, of some of the theory of that. So monotone system is one, oftentimes, so monotonicity suggests that you can compare things. So what you need is a partial order. You need to compare vector. In this case, so this will be my 2 n-dimensional cube, and I'm doing it for n equal 1, just because I can't draw 4-dimensional cubes, right? So this, and here's one natural order. I'm saying that this state, x, is less than or equal to y, right? Because component-wise, the components are ordered, the vectors are ordered component-wise. So the first component of x is smaller than the one of y, and similarly, the second component of x is smaller than that of y. There are other partial orders. This is the very most natural one, and it's actually the one that matters in this context. So you can imagine putting other order structures on state spaces, and there's theory to deal with that as well. We don't need that. We can stick to this natural order. Now, suppose you have a model and you solve the system for t units of time, any arbitrary number, right? Suppose there's a unique solution, and this exists. So this would be, maybe I'll use the flow notation, phi t of x, phi t of y, right? For any time in the future. A monotone system is one which preserves the order. The flow preserves the order. That means if I integrate the system from x and from y, which are ordered, and any later time they remain ordered. Their solutions remain ordered. It doesn't mean that they can go up or down. It just says the order is preserved. That's what a monotone system is. A strongly monotone system is slightly stronger. It's not really that important, I think, to go into the details of that at this stage. But it's certainly one that's monotone. So that's what this has. Now, interestingly, there are very simple graphical sign conditions. If you take any system on Rn, say, or on a subset of an Rn, X in Rn, it's easy to test whether the system is monotone with respect to the order I just illustrated. You just look at the Jacobian matrix. So you take the partial derivatives of the n components of the vector field here. That's an n by n matrix. If the ijth entry is positive or 0 for all I not equal to j, meaning for the off-diagonal entries of the linearized matrix, then this system is strongly monotone. Check. Do it mentally in your head. You'll see this condition holds for the system we have out there. Keep in mind we're working on 0, 1s to the 2n. We're not doing this in all of Rn, okay? Because if you try to verify that condition in all of Rn, it won't work. Okay. So that's what this last sentence means here. And that's what we will exploit. So first I want to formulate a simple dichotomy again, just like for the single patch model. And we can. That's the interesting part. Excuse me. So we need to define a new matrix. I call it S, which is, it looks kind of complicated, right? But P is that mobility matrix of humans. Diag R0, that's the R0 vector of the patches made into a diagonal matrix. D inverse, Q you know, and D inverse we need. Well, but that's this. Some people have already cursed me profoundly for using this kind of notation. It's a diag of what? Well, A times C. A is the vector of parameters. There's n of those A's, right? A times C is the vector A1, C1, A2, C2, A3. So it's component. It's the way you would like to multiply vectors. Yeah? And consistent with my desires, I'm also dividing here in that way, right? So I take two vectors and I multiply them component-wise. I know there's a notation for that with the little whatever notation, and I was too lazy to try and introduce it. So we do that for A times C and R times rho. Divide this, that's a new positive vector. Take the diagonal, that's what it is. Okay, so this looks very mysterious. Hopefully later on it will be less mysterious. Here's the theorem. Assume that PQ and QP are irreducible matrices, right? Then there's a dichotomy. If rho of S, rho is a spectral radius of this matrix. This matrix is a non-negative matrix, okay? The spectral radius can be computed for any matrix. What is that? That's the smallest disk radius that contains all the eigenvalues. Right? That's a spectral. So that's the radius of the smallest disk that contains all the eigenvalues, the spectrum of an n by n matrix. Interestingly, Perron-Frobenius says that this is actually an eigenvalue for the matrix. Okay. All right. Just a mathematical aside. But if that spectral radius of this just introduced matrix is less than 1, then the extinction or no infection steady state is the only steady state, and it's globally asymptotically stable. If the spectral radius is bigger than 1, then there's two steady states, still 0, 0, and an endemic steady state, which is strictly positive, actually strictly in the interior of the cube, and all non-zero solutions will converge to it. So this is the equivalent of what we saw for the single patch case, but now for n patches. Okay. So the same result holds. We did introduce one assumption, though, irreducibility of this product, and I want to spend some time on the interpretation of that. So did Michael define irreducibility of a matrix, or there's many equivalent ways. The one that I like best is really graphical. So if you take a non-negative matrix, you can associate a directed graph to it, right? So let's say we have a 2 by 2 matrix, 1, 0, 1, 2, something like that, right? And that's 2 by 2. That I'll associate a graph with 2 nodes, and then I'll draw edges if I see non-zero entries appear. So the first entry is non-zero, so I'll have a loop from 1 to 1. From 1 to 2, there's no directed edge because it's 0. From 2 to 1, there is 1 because there's a positive number here. And from 2 to 2, there's another loop here. That's very easy to construct, right? If you start with any non-negative matrix, you can come up with that directed graph. Irreducibility of the matrix is the following. This graph should be strongly connected. What does that mean? Okay. Strongly connected means if I give you any 2 nodes in this graph, then there has to be a path, maybe not a direct one, maybe through intermediate nodes, from the first one to the second one. That's what strong connectedness means. Yeah? So that's the condition I'm imposing for the matrix products PQ and QP, under which the theorem here holds. Yeah? Strong connectedness of these matrices, of the associated graphs to these matrices. Okay, so a little bit of interpretation. Yeah, the first part I just told you. So now ask yourself the following. So remember, malaria is an annoying disease because it doesn't go directly it has to go via a host. From the perspective of the mosquito, the host is the human. From the perspective of the human, it's the vector, or the mosquito. So suppose you have these end patches, and in patch I, there's one infectious human. One infectious human. And then all the other individuals, humans or mosquitoes, are susceptibles. Right? So I ask, can this single infectious human in patch I cause a secondary infection in patch J? So is it possible that it jumps? It can't jump, of course, but that the single infected human in patch I can jump to patch J. Well, if that happens, then it has to occur by meeting some infectious. I'm sorry. Let me break this down. So my claim is that the answer to this question is if the ijth entry of the matrix PQ is positive. Why is that? Well, look at this sum here. That's just matrix multiplication, right? The ijth entry of this matrix is just a sum. So PIK is the proportion of time that a human in patch I would spend in patch K, where it can infect a mosquito, a susceptible mosquito, that then may spend time in patch J, the one my target is at. And of course, my single infected human could have gone to any of the K possible patches that there are available for infection of a susceptible mosquito there. So that's the answer to the question, right? So now, strong connectedness really means that you don't go from I to J directly, but perhaps in an intermediate path, right? That's irreducibility of the matrix PQ. So what this says is if I start with a single infected human and only susceptible humans and susceptible vectors everywhere, then irreducibility of PQ is the same as saying that it's possible that that single infected human can actually cause a not necessarily secondary, but tertiary or quaternary infection in any other patch. It's sort of well mixed. You can't escape. Okay, if there's one there, it can get a hold of any other patch. Okay. And QP, irreducibility of QP, is the same, but now starting with an infected mosquito and asking this question: can that cause a secondary infection of a mosquito in another patch? Yeah.
The one infectious human in any given patch,
Yeah.
with an infection of another human, right?
Well,
In another patch.
not this. No, it has to infect a mosquito, but that mosquito can then go on and infect a human in the patch J. That's the thing. So it's not a direct infection. It has to occur indirectly. But the question is, can that happen? Well, it can if this number is positive. Yeah.
You are saying that the traveling of the parasite is transitive because the parasite can travel with humans by mosquitoes.
Yes. No, there's two conditions. Yeah, I'm only explaining the one. Yes, yes. Yeah, right. But I'm, well, this condition is one of the two conditions. And it's only from the perspective of infecting, starting with a single infected human. The positivity of QP, IJ, would be starting with an infected mosquito instead. Yeah. We'll get to the digraph in a second. I'm spending more, initially I hadn't spent time on this at all because people said, oh, but this is certainly true if P and Q are irreducible. Okay, and we'll get back to that issue later. Ask yourself, is that sufficient? If P and Q are irreducible, will the product be irreducible? Okay. All right. So what Gauthier was referring to is this last part here. So how do we test practically? If I give you a P and a Q, right? That's obvious, right? I can do the graph thing that I did over there. But how do I test whether PQ is irreducible and QP? Well, you construct a digraph. A directed digraph. A digraph allows a partitioning of the sets of the nodes. so that directed edges only go from one subset of the partitioning to the other, and vice versa. Not in them, not between themselves. So I'll give you an example so you'll understand quickly what I mean. So I'll have n. There will be n, 2n nodes in total, right? Here's one group. Here's another group. They're disjoint, and connections can only occur from nodes in this group to the other one, and vice versa, but not in between. That's basically, think of these as the humans, and these are the mosquitoes, and these are the end patches, right? If patch 1 can, a human travels to patch 2 where it can infect the mosquito, then maybe this, and then this, and so forth, right? So this is an example of a digraph, right? Irreducibility of PQ, yeah, so. Yeah, didn't I say that?
No.
Sorry. Yes, you're right, I didn't say that. Bipartite digraph. Yes, you're right. Bipartite digraph.
So far only the humans are.
No, there's a mosquito coming from here, right? Maybe my arrows aren't so clear. Okay, just imagine the following. So I want to give you a practical test, right? From this bipartite digraph, I will construct two graphs with n nodes. Yeah, the first one will only have these nodes. Now, how do I construct it? By just going and following this from here to here. There's a path. So erase all the connections here, but just replace that path by this, right? And so you do that. Well, maybe I should, my example is ugly as usual. But so all this stuff is gone now. Now I have found a graph with only these nodes, which is a directed graph. If that guy is irreducible, that's irreducibility of PQ. Similarly, I could do the construction over here and say I'm going to connect this guy with that guy if there's a path from here to there. And then forget this. Well, okay, you construct another, not bipartite, but just a directed graph, and you check irreducibility for it. That's the practical way to check. So it's easy. It's easy. It's a technical condition that we need to apply some of the stronger theory of monotone dynamical systems. It's not to say that the theorem would fail, but we can't really make predictions. That's the problem with this. So it's a sufficient condition. Okay. Now, here's some remarks about irreducibility of PQ and QP. So the first thing is what I... let's see, that's... So irreducibility of P and Q is not necessary for irreducibility of the products PQ and QP. Simple. Take P to be the identity matrix and Q any irreducible matrix, then PQ times QP and QP are the same matrix, Q, which is irreducible, but P isn't irreducible. It's the identity matrix, right? The identity matrix, its graph has just loops sitting at every node. That's not strongly connected. Okay. Okay, second thing, irreducibility of P and Q does not imply, that's the thing I mentioned earlier, irreducibility of the two products PQ and QP. Okay. It's not because humans mix well that the transmission will be able to mix well. That's what this is basically explaining. So take P and Q, the simple permutation matrix, 0, 1, 1, 0. The product is just the square of that same matrix, so it is the identity. That's not irreducible. Right? And then irreducibility of PQ. So one thing you can wonder is, well, can I get rid of one of the two conditions? So there's two here. PQ and QP have to be irreducible. And you could say, can I not drop one of them? Maybe it implies the other, right? And this is an example that shows it's not the case. So I can take P and Q to be this. And they're all stochastic matrices, right? I'm not trying to cheat you into something here. PQ is a positive matrix, which is certainly irreducible. But QP is this, and that's not irreducible. So you cannot drop one of the two. You cannot say that one implies the other condition. Okay, that's as far as the conditions go. Okay, so here I get to that inverse problem. Yeah, so let me just come back first and say, we stated this theorem. At the end, I will sketch the proof using theory of monotone dynamical systems. Okay, I will just give the sketch of how you prove this. My question to Michael, who's actually writing that now in silence, is to come up with another proof based on his method, because I think it might work. The talk he gave. The question is, what's the Lyapunov function for the single patch model, right? I haven't designed it because I'm using monotone dynamical systems, but it's a two-dimensional system. It might not be too difficult to find. All right. So we postpone the proof of this and now turn our attention to something else. Is the following question. Suppose the spectral radius of that magical matrix S is bigger than 1. So we have, by the dichotomy, that there's a unique, globally attracting endemic steady state. So you could measure, you could go in all the patches and count how many people have malaria, right? So that means you can measure X bar, or at least estimate it. What would be the additional model parameters that we need to find all the patched reproduction numbers? That's the question. So that's the inverse problem. I want to find a vector R0 based on the measurements of infected people. That seemed like a reasonable question to ask. So that's not that difficult. This is the reason why I was doing these extra manipulations with the parameters earlier on, in order to exhibit the dependency of the steady state on the vector R0. So I'm rewriting the steady state equations here. And so you're trying, X bar is given, and you're trying to find this vector R0. So this is a matrix times the vector R0 is some other matrix, right? So you just want to invert this matrix and you're done, right? The problem is it depends on Y bar, which you don't know. That's the number of infected mosquitoes everywhere, but you can hardly go and count and poll the mosquitoes for who is carrying the infection. Right? So that's why we have to break this down in 2 steps. Turns out you can find Y bar in terms of X bar by solving this equation. That's not so difficult, because you can, yeah, again, these monotone functions come into play. So you can find Y bar as this, where Z bar is that matrix. It involves X bar and some model parameters, but nothing else. And then plug that back in here, and then invert this matrix, okay? Assuming it's invertible. So if you look at that matrix A, it's a diagonal matrix with strictly positive diagonal elements here, strictly positive diagonal elements there. So invertibility of A is just equivalent to invertibility of P, of the human movement matrix. That's it. That's the condition. That may not be true. So here's a homogeneously mixing population that spends 2 patches. It spends 50% of the time at home and 50% in the bar, right? And that's clearly not invertible, so it won't work. Okay, what else do we need? Well, we need, so I'm listing here what the other parameters are that we need in order to compute, to compute the vector R0. So I need the vectors R and mu, the recovery rates of humans, but that should be in the literature, or people should have reasonable estimates for that. The death rate of the mosquitoes should be reasonable as well. The vector alpha, we explained what that was. That's something you could test. I don't know if it's been done, but You look at a susceptible mosquito and let it bite and see how many infections it could receive in its life. And then here's the problem. That's why I put it in red. You need the matrices P and Q. Those are the mobility matrices. For humans, it's probably doable, or to estimate some of it, right? You can say, well, these villages are big. This village will never visit that, so that entry will be 0, or this will be very small, and so forth. But Q is the movement of the mosquitoes. That's far more difficult, but that's what we require. And then the vector rho, which is nothing special. It's the ratio of the total number of humans in the ith patch over the first patch. You know how many people are around, in principle. Now, compare this to the original definition of R naught, because you don't have to do what we're doing here. You could just plug in the parameters in the original definition, right? Now, the bigger problem there is that you need MII, which is the number of vectors over host, which means you need the number of counts of mosquitoes for all the patches. We don't need that. So it's somewhat imbalanced. On the one hand, we require these mobility patterns. On the other hand, we don't require counts of mosquitoes, which is a good thing. Okay. Now, clearing the infection, how do we do that? Well, we make the spectral radius less than 1, but now the spectral radius is of some matrix which is complicated, okay? I'm just repeating it here. So we'll break it down in 3 cases where only one type moves, either humans or vectors, and then when both move. Okay. If the humans only move, then Q is the identity, and S, this matrix becomes much simpler. It becomes P times the diagonal of R naught. Okay. And you can prove using Perron-Frobenius theory that the spectral radius will always be squeezed between the minimal patch R naught and the maximal patch R naught. That's a sensitivity result that's quite remarkable, but it says essentially the spectral radius of a non-negative matrix, which is an eigenvalue, I told you that, is actually increasing with respect to the entries of the matrix. That's quite remarkable. For non-negative matrices, this is not the case. The spectral radius might decrease. Okay. And a consequence of that allows us to prove this. Okay. Oh, the proof is actually here. Yeah. No, so this is saying no matter what P is, rho of S will always be in yeah, of course. The fact that the dominant eigenvalue of P will be 1, yes. So yeah. And then is multiplied by this diagonal, it plays a role, definitely. Yeah, yeah. So actually, the proof is here, right? Right. So what's the effect of multiplying P by a diagonal matrix non-negative entries? That's multiply each row by the corresponding diagonal entry of the diagonal matrix. So if I take all these diagonal entries to be the minimum one, that matrix is lower bounded by the original matrix, and therefore we have that first inequality here. Yeah? And the second one is replacing it by the maximum. Okay, and these lower and upper bounds are actually achieved for particular P matrices. So these bounds are tight. This is saying that the spectral radius is bounded in this interval, and it can achieve them. It can achieve them. Now, the proof shows that these upper bounds are achieved for non-irreducible matrices, but by continuity of the spectral radius, you can always approximate this as close as you want by an irreducible one. Okay, so in practice, you're stuck. No matter what you will do, if you don't have control over the mobility matrix, there's not much control you can do. You cannot make it smaller than this, and that might be an issue. So then the next step would be, well, we'll see. Okay, so here's some consequences of that result. If all the patches are sinks, right, that means all the R naught i's are less than 1, then the maximal one is also less than 1, right? Then rows of S will always be, no matter what P is, no matter what the matrix P is, will always be less than 1. So if that says if all the patches are sinks to begin with, no matter how humans move, if mosquitoes are fixed, the infection will be cleared. And that justifies the classical control approach, which says we need to identify the sources and try to make them into sinks. That's the idea. Because if you do that, you will guarantee that the infection gets to be cleared. The question is, can you do something better? Do you really have to make every patch, which is a source, into a sink? Okay. All right. If all the patches are sources, that's the converse, really, and all the R naughts are bigger than 1, so is the minimum one, then the spectral radius is always bigger than 1, and no matter how the movement is, you can't do anything. Infection will persist. And so this conservative control strategy I'll just talk to you about before. Okay, here's just a simple numerical example to show that the control strategy to make everything less than 1 in every patch is not necessarily the right thing to do. Here you have an R naught with a patch. The first patch has an R naught which is bigger than 1, so it's 1.5, and the second one is 0.5. So the first patch is a source, and the second one is a sink. If the mobility matrix P is this, you can calculate the spectral radius. S is, I remind you, S is just P times the diagonal of R naught, right here, is less than it. So the spectral radius is less than 1. So although the first patch was a source and the second was a sink, the infection would be cleared on its own for this mobility pattern. You shouldn't do anything. Just let it take care of itself. If the mobility matrix P is different, if it's that, then rows of S is bigger than 1 and infection persists. And so in this case, you should do something to clear the infection. But it just shows the conservative nature of trying to focus on making all the sinks into patches, because that's what's traditionally done. People want to go into the villages and put bed nets there and so forth. What this is showing is it might not be necessary, so spend your resources on other things. Okay, when only the vectors move, similar kind of result. It's a bit more complicated because the matrix S doesn't simplify as nicely, but you have essentially the same result. You have to do a little bit of linear algebra to get to it. So the spectral radius is always, no matter what the mobility pattern of the vectors is always squeezed between the minimal R naught and the maximal R naught. Okay, now comes the interesting part, when both vectors and humans move. Then we cannot simplify this magical matrix S, but we can find bounds that are illustrated here. So I introduced a new vector D. That was that funny vector, A times C divided by R times rho. That's a vector. I take its minimal component, and I multiply that by the minimal component of the vector R naught divided by D. And then similarly for the maxima here, those are the upper and lower bounds for the spectral radius. And again, they are achieved for appropriately chosen mobility matrices P and Q. So this one can be achieved as well as this one. So here is perhaps the most, well, shocking thing is that the conservative control strategy here, if both vectors and hosts move, it may fail. Here's the examples. So you take an R naught, which is 1/2 and 1/4. So suppose we've already achieved our goal of making all the R naughts less than 1, and we think we're home free, right? That's what, standard practices would do, perhaps. and our D vector turns out to be this, okay? And they can be chosen independently, so I can make up these numbers the way I want it to. And now, just evaluate these lower and upper bounds. Well, the lower bound turns out to be, yeah, this is no, I'm sorry. I'm only evaluating the upper bound. So the upper bound, if you calculate this D max, well, D max is 1, and R naught over D is 2 and 1/4. So the maximal component of that is 1/4. Maximum of 2 and 1/4 is obviously 2, right? So this says there are mobility patterns P and Q that are arbitrarily close, for which the spectral radius of rows of S is arbitrarily close to 2. So although you made your patches locally into sinks, the movement of the vectors combined with that of the hosts makes that the infection still persists. Okay? That's probably the main practical message, that when both move, those strategies have to be evaluated. Okay. There's a sort of dual here. So the disease can also be cleared even if all the patches are sources. That depends on the mobility. So it could be that all the patches are sources. If they would be isolated, you had a malaria infection, but by connecting them appropriately, the infection will be cleared. Right. That's the conclusion of this. So, well, there's not a lot left, a few more pages. I want to sketch the proof now of the main theorem, right? Which was this dichotomy here, this theorem. So either we break or we just keep going and we're done in 20 minutes. It's up to you. Are there any questions at this point? Suggestions on breaking, or it will take maybe 10, 15 minutes. Yeah. And then we'll be done. We'll be done early, I guess. Okay. Okay, so I already told you that the system lives on the cube, the 2 n-dimensional cube, and is strongly monotone. And at 0, 0 is always a steady state. You can read that off immediately. So it's kind of always a first step to linearize at 0, 0. So we get the Jacobian matrix. That's that matrix consisting of those partial derivatives evaluated in 0, 0. And so the claim I'm making here is that that matrix is 2n by 2n, right? I'm claiming that that is a stable matrix, meaning all its eigenvalues are in the open left half plane, if the spectral radius of S is an n by n matrix, is less than 1. And unstable if it's bigger than 1. Okay, so here's the proof. That comes from an application that comes back over and over in math biology. It's one procedure to compute essentially basic reproduction numbers, and that procedure is nicely introduced in this paper by Van den Driesch and Watmu. So you write the Jacobian matrix as a difference of F and V. V is a diagonal matrix with positive diagonal entries, and F is all the other stuff. So these are recovery and death rates, and these correspond to infection terms. Okay, and then so you can, what they show is that J sub 0, 0 is a stable matrix if the spectral radius of F times V inverse is less than 1, but unstable if it's bigger than 1. That's a theorem. Okay. We're going to apply that. So we calculate F times V inverse. That's this matrix. Okay. So here's a little lemma or proposition in between. That says the following. And this is where I use the actual, well, for the first time, the irreducibility of the product PQ and QP. Those are the main conditions in the result. So if you take any matrix C that's non-negative, but which has 0, it's in 2n by 2n matrix. It has a 0 n by n block on the diagonal, and the matrix A and B here. Yeah. then that matrix is irreducible if and only if the product of these two in both ways, both directions, is irreducible. What that is the proof I was giving you here, of that graphical proof of the collapsing of the digraph, bipartite digraph, into two separate ones. And if this matrix is irreducible, meaning if these two products are irreducible, then the spectral radius of C squared is equal to the spectral radius of the product of either one of these two matrices. Okay. This is a little proof based on the Perron-Frobenius theorem and on the understanding of the notion of irreducibility, but it doesn't take much. But it's crucial in order to continue here. So we're going to apply that to F times V inverse. That was this matrix that has this structure of the C matrix, right? So it has these two blocks. See that here? This is my A and my B matrix. And what were the conditions? That this times that in both directions has to be irreducible. Now, irreducibility is never affected by multiplying by diagonal matrix on the back or the front. So you can actually forget about them and pretend as if there's here a P and here a Q. And so irreducibility of AB or BA is the same as irreducibility of PQ and QP. Okay. All right. And then we apply the results. So the spectral radius square of FV inverse is a spectral radius of S. That's that matrix. That's the product of either ones of these. But you can then, you know, well, the product of these two is not S, okay? But the spectral radius is invariant on the, so the spectral radius of a product of two n by m matrices is, you can commute the product without affecting the spectral radius. That's what I'm saying, in order to simplify it to the matrix S. And this is where that mysterious matrix S came from. Okay, so that's a local linearization result. So now we want to move to the global stability proof. So for first case, what if that matrix S has a spectral radius less than 1? What I want to show is that the origin is the only globally asymptotically stable steady state. So the first thing I want to show is that there are no other steady states possible. Okay. Well, suppose there is one. Well, we can write the system has a special structure. It can be written as some matrix A with special structure times the vector of steady state vector x bar y bar equals 0. So if you, well, you don't have it here, unfortunately, but trust me, you can do it. And the special structure this matrix has is it's a Metzler or quasi-monotone, or there's various names that are being used here. So it's a matrix that has non-negative off-diagonal entries. That was the condition for monotonicity that I gave you earlier on. Okay, and it's those entries are decreasing with the state. So that means that that matrix here is going to be or less than J sub 0, 0. J sub 0, 0 would be the corresponding matrix at the linearization at the origin. So entry-wise, this matrix at that imaginary steady state is going to be ordered like this. Perron-Frobenius now tells us that the dominant eigenvalue, the leftmost eigenvalue of this matrix has to be less than that one, right? But that one is a stable matrix. That was equivalent to this condition. So that would mean, no, I'm sorry. I messed up the proof. Okay, this condition says that that matrix has a 0 dominant eigenvalue. Okay, because this is 0 times that same vector. So, and that's a positive vector. So you know then that 0 is the dominant eigenvalue of this matrix. But because of this ordering, J should have a strictly bigger dominant eigenvalue, which is strictly positive. That's a contradiction to this, which was equivalent to saying that that is a necessary and sufficient condition for stability of J 0, 0. Okay, so there can be a non-zero steady state in the hypercube. Now you evaluate the vector field. F is the vector field of the system in the northeast corner, and it points southwest. Right? So I'll make a little picture. Here's the vector 1, 1, right? Okay. The vector field points strictly inside. That's what that condition means. Okay. The system is monotone. So the solution that starts here decreases instantaneously. Yeah? The decreasing function has to converge if it's bounded below. It has to converge to a steady state. There's only one sitting here. So it has to, this solution has to converge to the origin. And then monotonicity says any other solution that's squeezed between this initial condition and this must stay below that solution. So those must also converge. That's the main idea. Okay, that shows global stability in the first case. The second case is a bit more complicated, but exploits the exact same ideas. So if rho of S is bigger than 1, we start again. So now we linearize again at the origin. But now this matrix, Jacobian at the origin, is unstable. So S, the rightmost eigenvalue, has to be positive. Okay. So the vector field of the system evaluated in small scalars of that vector, dominant eigenvector V, has to be pointing northeast. Okay. And the vector field in the northeast corner still points south. That's something you can evaluate. So you have close to the origin, it points like this. At 1, 1, it points like that. Yeah. So those the solutions on those initial conditions decrease and increase. They're bounded, so they must converge to a steady state. Well, let's call these steady states the minimal steady state and the maximal steady state. You can show that they must be ordered. That's by monotonicity again. And there are so-called connecting orbits. So there's an orbit connecting the origin to that minimal steady state and the northeast corner to the maximal steady state. So these two solutions go like this. The challenge is now to show that these two steady states are actually the same thing, that there's only one. Once there's one, we can apply the same sandwich argument to then show all solutions go to the unique steady state. So that's what the claim is here, that those minimal and maximal steady states are the same. How you do that is by arguing very similarly using the comparison, the sensitivity result as before. So you can write that A times this minimal steady state times itself is 0, and the same for the maximal steady state. But these matrices are ordered entry-wise, right? But these two equations say that 0 is the dominant eigenvalue of both, right? And that contradicts the Perron-Frobenius theorem that says that the dominant eigenvalue of the lower one has to be strictly lower than that of the higher one. So that concludes that there's only one such steady state in the interior. And then the monotonicity, I already said that, implies that everything converges to that unique endemic steady state, and we're done. And I think that's it. So thank you. Questions? Yeah.
So you have these two matrices, the PQ and QP.
Yeah.
And which seems give an idea of the transmission between a human and the transmission between a vector, right?
Well, P is the matrix that gives the proportion of time that humans spend elsewhere. So the ith row says the human residence of the of patch I spend this amount of time in patch J. That's the Pij entry. Q does the same for the vectors.
Yeah, so the matrix is PQ, QP.
Yeah.
Thank you. So if I understood well, at least,
Yeah.
the matrices PQ and QP give you an idea of the the possibility to transmit from one human to the other human the disease, and from one vector to the other vector, right?
Well, not again. The humans don't infect humans. They have to go through
Indirectly.
vectors. But exactly.
Yeah.
So it doesn't. It says how a single infected human in a certain patch could indirectly infect a susceptible human in another patch. That's the product of PQ, the ijth entry, being positive, captures
Okay.
that. And 0 means it can be done.
Because now my question is the following: your theorem is valid whenever PQ and QP are both irreducible.
Yes.
But from the human point of view, say, if PQ is irreducible but QP is not, is there a difference from the point of view of the transmission of the disease?
Yes. So
what happens in such case? Do you know?
if one of them is irreducible but not the other one,
yeah, exactly.
Is that your question?
Yeah, exactly.
Okay. So let's say PQ is irreducible, then that means any infected human, starting with a single infected human in any patch, no matter where, can, through secondary, tertiary, and so forth, infections lead to an infected human in any other patch. The one QP not being irreducible, meaning it being reducible, means you could start with a certain patch where there's an infected vector that cannot reach another patch and introduce an infected vector there. That's what that says. That's it. So there's a lack of mixing. You know, so it's sort of saying you could be starting in a very idealized initial condition for which it's not possible that the infection will spread everywhere. That's all that this is saying. Again, I told you this. I need that condition for technical reasons. Okay, I'm not saying that. I don't know what the theorem would look like, but I think it's more complicated. You probably don't have a simple dichotomy there, where I mean, in some cases you might, in others you might not, but you can't make it as black and white as you can under these irreducibility conditions.
You're trying to say that reducibility is good.
No, I was wondering, because this is something that cannot be really justified, what happens for the mosquito displacement. And so...
Well, I mean, you could tag mosquitoes and see where they fly to. I think you can do that experiment. I mean, in fact, if you have a patch network and there's an endemic steady state, then these conditions must hold, because they have started somewhere in a single patch, presumably, and gone through infecting all the other ones.
But isn't it possible to reduce the number of patches of the mosquitoes and to have a stability result? You see,
So okay, so there
with
are
a smaller,
other models that So what we are saying is mosquitoes and vector and humans are cohabiting. They're in the same patches. There are models that say, well, they are different and they may have different number of patches, right? So you have physically distinct geographical patches. We haven't introduced that, but that's something you could add to this. And my guess would be a similar result could be possible to prove, but again, I would need some sort of irreducibility in both directions, from the mosquito point of view as well as from the vector point of view, in order to get the simple dichotomy. Yeah. Oh.
Hey, I think one of the main point is that the reason why you need both products to be reducible is that the way you construct your model is that only susceptible ones moves. While
No.
if you allow
No, no.
infected ones, then you wouldn't need. Because in
No.
your model, only the susceptible ones are moving, either human or
no,
vector.
there
right?
are some issues. Okay.
Because then, with this hypothesis, yes, you cannot move the infection from one place to another unless you have irreducibility on both products. But if you allow humans, for instance, infected humans to move, then they can introduce to other places, even though the mosquitoes don't move.
Okay.
You see, and this actually happens. It's how Zika was introduced in Brazil, for instance. It was from infected humans traveling and not mosquitoes.
Yes, right. Okay. So maybe I should say yes.
Yeah, if you allow in our model to have infected humans or vectors to move, then I believe that you wouldn't need both products to be reducible. Only one would suffice.
Yeah, I would have to think about that. I mean, that would change the model, I guess. And I can't predict what will come out. Yeah, Gauthier.
Yes. I suspect I have another proof of your last theorem. I suspect that, I have to check it, but that your system is sublinear. Or if you prefer, another way to say it, it's if you look at the Jacobian is decreasing when you increase.
Absolutely,
and after you have this famous theorem of Hirsch, okay, you're saying the same thing.
Right.
Probably.
Yes.
Yeah. And so when your disease-free equilibrium is unstable, you have one unique equilibrium and attracting everybody.
It's a trichotomy. You could, in that theory, you could also have explosions, but this one doesn't because it's on the cube, right?
Yeah, it's just I don't want to make computation,
Yeah. No, you're right. So there's Gauthier is referring to some theory. Where I've seen it is in a paper by Hal Smith, but I've seen other people. Krause has a book. Very recent book with a bunch of Nussbaum and Lemons. They do it for discrete systems.
Yes, but the best reference for this theorem is a paper of Hirsch.
I don't even know.
Yes, in '84, and which is the dynamical system approach of something, and the proof is very very small.
Yeah, I actually saw that when I was a grad student.
Yeah,
but that's
right. Okay, we can talk after.
Yeah.
Okay.
Yeah. But so before, I mean, it's kind of in my first versions, I didn't comment at all on irreducibility. I just stated it and didn't discuss it at all. But then I would get questions like the ones that were addressed in my slide on cautionary remarks. And I started thinking, what does that condition really mean now? Because I know it helps me mathematically, that's one thing, yeah. But what does it really mean from the infection point of view? And I'm trying to be as clear as I can to say what it is. I'm not saying if that fails that I can't prove anything anymore. I just don't know. The theory I'm using requires those irreducibility conditions. I spent perhaps too much time on emphasizing what do they mean, what do the conditions mean, but that was just for, teaching purposes, I guess. I don't know. Yeah. Yeah. Sorry.
Okay, just a couple of comments regarding to his comment. You can actually see your model as you can understand the P and Q as the infective and susceptible moving, and the mosquitoes are stopped. That's one way of interpreting your system.
Yeah, there's different ways of thinking about it.
So you can think about that. I mean, so you can also think that you have two different networks: one for the susceptible, one for the infected.
Yes.
And the mosquitoes are not going anywhere.
Yeah.
So, and the second comment is that you can have P and Q reducible, and both products irreducible. Which is also and the interpretation, I think, which is
and then the theorem applies.
And the theorem applies. That's definitely interesting.
Exactly.
And the point is, if you think that, I mean, really what you're requiring is that the bipartite graph is irreducible, And the way of think that is that if you then think of mosquitoes
Yes.
and humans as just like, I mean, animals, human beings, or I mean just beings, that means that the network of the system that you obtain is irreducible for the multi-group. So that's so
Exactly.
that falls in the
Absolutely. Yeah.
So that's a way of thinking that.
Yeah.
Just two comments.
Yes, I agree.
You didn't give control measures for the situation on both P and Q, sorry, the hosts and the vectors moved. Am I right? You just said that the other control measures wouldn't.
Yes.
be-
So my focus there was on. So traditionally, the focus of measures has been on try to identify the sources and try to get those to become sinks. How you do that is by bed nets, spraying insecticides. This, although I didn't highlight it enough, says you could actually make travel patterns different and affect. So my results were more from the point of view, let's take any possible P and Q, any possible movement, what would the old control measures achieve? That was my main goal. And so I showed, well, sometimes it might work, but not always. If both move, there might be cases when you've eradicated, based on single patch thinking, the disease, but because of the pattern of the movement of both mosquitoes and vectors, the infection is still there.
Did you have any hint about completely new ways of control that use the movement of both hosts and vectors?
No, well, no. So in some way, it's buried in the proofs. So so the bounds that I showed you, right? There were 3 results, but each time there was an upper and a lower bound for the spectral radius of S, which is a quantity that matters. So, and the proof then shows that which mobility matrices achieve those bounds. So the lower bound is the lowest you can get. If you choose the mobility pattern close to, by restricting travel, for example, close to the pattern in the proof that achieves the lower bound, there's your measure.
So the measures will pass by restricting the movement of hosts or restricting the movement of vectors, and after that using conservative measures.
Yeah, so hang on. So what I'm saying is, so you have to find a P and a Q such that this matrix, which depends on P and Q, it's not explicitly mentioned, but equals that value. And you can always find such. I can show what that is. It's well, yeah.
Okay.
But that will mean restricting travel. That basically will say you stay home. All these stay home or cannot travel there anymore, and that's not going to happen. I mean, that's the big scare, right? With Ebola, and oh yeah, suddenly one nurse flies to the States and the whole world goes crazy because maybe we should cut down, prohibit travel, and we have quarantines and. But that's in a sense, yeah, that's a control measure. But go ahead and implement it. That's not going to be easy, I think.
Then I understand that you want to transform a source in a sink, right?
That's a classical thinking.
Right.
What I'm saying is that may not be enough.
How the model works for instance, for a mutant mosquito which resists to the controllers. Suppose you then how the robust of the model.
I mean. That's a very good question, and I haven't really thought about it. So you're saying, suppose suddenly a mutant mosquito is introduced that's much more resilient or somehow to pesticides, for example. Well, that's basically saying that there's, so the model parameters to some degree, except for the P and Q, describe the environment. And what you're suggesting is a change in that environment, because maybe the biting rate suddenly of that super mosquito went up by 20% or something like that. That could affect clearly the results. But if you're still in this model, in this context of this model, you could still use the results. I wouldn't know how to. Or maybe you're even asking, can you add multiple mosquito populations to the model, which may mutate from one strain into the other, as well as start moving around on the graph? And that's that might be a interesting question. Yeah, I haven't thought about that. Yeah. Okay. All right. Thanks.
Thank you very much for this nice talk. So the sessions are over today. Maybe we could have done a fourth one. I don't know. Maybe last time. You seem to be in very good shape. So we meet tomorrow at 9 for the first plenary, which will be Mercedes one, I guess. Thank you very much for being here. See you tomorrow.